Okay, folks, we can finally get started. Sorry for the technical difficulties, and we still kind of have a little bit of the edge off, but we'll be okay. I'm Andy Gross. I work for Linaro. I'm part of the LITE team, which deals primarily with IoT devices. For the past, 6-9 months, something like that, I've been working on Zephyr for some of the ARMv8M support and some of the security changes that came in before the ARMv8M work, some of the user space stuff. So you'll see, notice a nice abrupt change to the template. I only kept the front slide to their template and then switched back to a Zephyr one. But anyway, the agenda for today, I'm going to talk a little bit about what T means for microcontrollers. We'll talk a little bit about the hardware requirements that you may need for implementation of execution environment. I'll talk about the Zephyr support specifically for ARMv8M, and there'll be a little bit of a v7M information as well, because we do have some configurations where people want to have multiple cores doing a trusted execution environment versus an ARMv8M. And I'll touch on the multiple image complications, which if you were able to attend David Brown's presentation yesterday about MCU boot, this also touches on some of the things that he brought up in his talk. And then we'll talk about some of the current work items, things that are coming down the pipes that are actively being worked today. So, trusted execution environments, there are some solutions that are currently out there in the ecosystem. Synopsys has their Secure Shield for their ARC processors. They are currently working on adding support into Zephyr for that. We have the TFM, which is the ARM trusted firmware for Cortex M. And then there's also some proprietary multi-core solutions out there. One good example is probably the Cypress PSoC. They have a multi-core with I think it's an M0 that's designated as a security processor. And they have some IPC where they go back and forth to do calls to do certain secure functions. And there's probably some other ones out there that people have proprietary designs for. So fundamentally, when it comes down to it, what are we trying to do? We're trying to keep from leaking information, and that can mean a lot of things. Whether it's a key or a cert that you have stored off somewhere, some information you don't want accessible from applications. You may want to do something with the information, but you don't want to expose it directly. And that's really what all this is about. So how can this be done? So ARMv8M came out with a solution where they've separated some environments. There's a secure and a non-secure environment. And you can actually divvy up the resources on the board, whether it be the flash, the RAM, the peripherals, and only have access from secure or non-secure. If you're running non-secure, you can't access the secure components. If you do, you get a fault. This requires some access controls on the peripherals and also on the memory space. So you can kind of think of it somewhat like a memory protection unit, except maybe extended a little bit. But for the peripherals, you can actually flag a peripheral as being owned by the secure or the non-secure. And if you try to access it, of course, you'll get a fault. For ARMv7M, however, people do this through the use of multiple cores. And so what you have is you actually have a physical separation of the peripheral. And they may be on the same chip, but one core may have its own memory and flash, and the other core may have its own. And you may have some IPC, so if you're talking to the secure processor, it has its own set of resources that are not directly accessible by the non-secure processor. And that's how they do that. You may have some shared memory and things that you can use for your IPC, but primarily you're going to be storing your secrets off on the secure processor's resources. So, touching a little bit on the ARMv8M specific hardware, so the things that they added. So there's two types or two versions of ARMv8M. There's the mainline and the baseline. And there's also what they call security extensions. So the mainline is a v7M compatible processor. The baseline is a v6M. The differences are there's some instructions set differences. And I think the V8M supports DSP extension and gosh, I can't think of anything else, but there are a few other small differences. So they added the secure non-secure environment. There already existed a privileged and non-privileged mode, and this is true on the V7M and V8M. And I think it's also an option in V6M if you have that extension. They added a security attribution unit, and this is where you can actually specify memory ranges, flash, peripheral address space. You can actually set this to be accessible by one or the other, and actually also set the read, write, access permissions. If you're a SoC vendor, you can implement an IDAU, which is the implementation defined attribution unit. So that's just it's like an SAU, it's just implementation specific for that chip for what the SoC vendor wants to do. And then there's also some memory protection units that were added. I believe they're optional, but you have an MPU on the non-secure side and you also have an MPU on the secure side. And they use that, I'll get to that, but you can use the MPUs to firewall off some of the secure areas if you want to actually partition your secure execution environment into multiple partitions. So Zephyr support currently, as it stands, Nordic did a bunch of work in getting the base architecture support for the baseline and mainline in. So baseline is the M23, mainline is the M33. If you hear people talk about these, that's what they mean by them. There's support for the memory protection unit, and also what was really nice, ARM did two things. One, they fixed their memory protection unit to be a little bit more user-friendly. In the V7M and any SoC manufacturer who decided to use the base vanilla ARM implementation, it required power of two regions, which is very, it's a pain. What that meant is not only did you have to size your things by power of two, you also had to actually start your region on a power of two. And if you weren't careful, things could actually slide into an area where it actually wasn't covered by your region. And that could either open up things to be accessed by non-secure, or you could very easily exceed that in fault, thinking that you're doing the right thing. The other thing that they did is instead of using one of the regions for a stack limit, which is what we do currently on the V7M, they added a stack limit register, which I believe is optional, but it's really nice because when you're running, you just set the stack limit. That will actually do the protection of your stack for you instead of having to deal with the protection unit. So that's pretty nice. The other thing that was added, support for the MSE, which is the security extensions. You have to use a newer compiler that actually has the support for that. And the option is that -MSE. And if you pick up one of the ARM GCC compilers, I think it's 2017 Q4 or newer, you'll have support for that if you want to play around with it. Where this comes in is that if you want to create the veneers or some of the security features, you have to use that option. The reason why is because they added an extra linker region that's called the secure non-secure callable. And what that allows you to do is when you actually do your transitions from non-secure to secure, you have some wrappers that are built in that area where you jump into that, and then that allows you to jump into the secure execution environment. Another thing that was added was the secure library stub creation. So if you've gone out and looked at TFM or looked at Zephyr, when you want to run an environment where you have a non-secure and a secure image, if you want to do secure functions, you actually have to create a stub. This is the thing that allows you to actually progress across the boundaries. There is support in Zephyr to create that. And I'll kind of talk in the next few slides about, well, you have a lot of choices when you decide what you want your secure code to be. You can use TFM, you can use Zephyr if you really wanted to, or you could just write your own. But there are some specific things that you have to take into account if you do that. Lastly, we have some SDK work in progress. So with the change in the compiler, the current Zephyr SDKs don't have a compiler that supports this. So you either have two choices. Well, you have one choice. You have to use an external compiler. We don't want that to be the case. We want an SDK update, and we want people to be able to pull that down and just use it like they would today with Zephyr. We don't want people to have to go around and try to find tool chains. So I'm going to touch on, the next 3 slides are going to touch on how ARM, at least in the past and even in the present, kind of describes how these systems are going to be set up. And this will become clear a little bit later, I think, when we start to talk about how the system works together. So if you've gone to any of the ARM presentations, they'll talk about level 1, level 2, level 3 of PSA. And what that means is that if you're running ARMv8M, and even if you're not really, but this slide shows an ARMv8M, you're going to have a separation in the system. You're going to have some user application code which is going to run in non-secure. And then you're going to have a secure image that's running on the side that has some set of functions that you want to actually do. That may be, you may have some resources over there like a key. You want to make calls over to encrypt some information. You may want to sign something. The hash line in the center is the separation between the two. On an ARMv8M, this is a context switch. This isn't actually IPC. I think PSA now specifies that it's IPC, but that on the same processor, that's kind of an odd thing to do. But in level 1, what happens is you have your non-secure application on the left. You have all the secure functionality on the right, and there's no separation between any of the secure partitions. So they all have access to the same resources. An SPE is a secure process environment. The SPM is the secure partition manager. The SPM is supposed to be the one that when you switch context sets up all the security the way that you want it to be. If you transition to a level 2, you'll see now that there's a separation between the SPM and all the secure functions. And then if you take it even further, you may have separation between all of the secure partitions or the secure functions. And I think yesterday, if you went to the presentation, you would have seen, the ARM presentation, you would have seen something similar to this. So when we were talking about the hardware before, I mentioned the MPUs and the SAUs and the IDAUs. When you are actually firewalling off these things on the right, I think this is where the MPU is probably going to come in on some of these things. You're going to want to set this up to actually separate out some of the partitions. And when you're running in one context versus another, and when I'm saying context, I mean even within the secure context, you may be running on one of these functions. You only have access to a certain amount of the resources. Now, currently in the TFM, we only have support for level 1. So when you do the transition, everything on the secure side, you have access to everything. So that's something to keep in mind. Now, in the future, I think they're going to be adding in support for these other levels. So in a single core implementation, and this is true today in Zephyr if you try to run this, this is an ARMv8M. You're going to have your application code. You're going to have some API that you're going to call that needs to call down into what are called what a lot of people call the veneers, but really they're stubs. Those stubs reside in the secure, non-secure callable region. That's when you go down the stack, you eventually reach the point where you actually make the transition across and you access one of the SPEs. Once you're on the other side, the code on the other side does whatever function you want it to do. In the current TFM, this is a blocking synchronous call. So you make the call, it runs to completion, you come back. If you do something that takes a long time, well, too bad. And in one of our current boards that we have that runs fairly slow, we were doing something that was taking seconds, so then of course you get back and your systic is completely wrong. So yeah, that needs to be dealt with, and I think in the future there's going to be some improvement there to deal with that, because I mean we're talking about an RTOS and making these synchronous calls. You can't block for a long period of time. You have to actually deal with other things, and if you have things that you need to deal with, then you have to start thinking, well, then I have to start switching or moving things over to the other side because it's able to handle them. So yeah, those changes need to be made, and this was something that was brought up in Linaro Connect, I think in one of the ARM presentations. I'll say now, if you guys haven't seen some of the presentations, the previous ones, or even the one yesterday from ARM, please visit them and check them out. There's a lot of information in these that's very useful to understand how some of these things work. So in a multi-core implementation, which this is also being worked on right now, it's very similar. The difference is instead of having a context switch on the same processor, you actually have open amp on the bottom with, the stub is going to, the API is going to be the same, but once you get below that, instead of doing the stub and doing the transition to the different context, you're actually doing an IPC call across open amp, which utilizes some mailbox hardware and maybe some shared memory. This would be true whether for the multi-core, and this is something where I think we have one of our boards that has 2 M33s on it. We're going to be modeling that. We do have some current V7M hardware, the PSOC 6, which we're going to be doing the same thing. So the idea is that TFM is going to run on not only ARMv8M, but also run on V7M as well. The only difference, of course, is going to be how you do your transition. So going past some of the architecture and how things are going to work, when you actually create your images, you run into kind of one of the first problems, which is, okay, how do I load the system? If you're running secure and non-secure, you have 2 binaries. So that means you have to have a bootloader. So regardless of whether or not you're going to use TFM on the secure side, you have to have a bootloader. The other thing you have to have is you have to actually implement some of the security configurations. So today when you build Zephyr, you can build Zephyr to run secure, single image, and you can load it and run it just fine without any bootloader, anything. You're not getting the full benefit of having the separation and the application being on the non-secure side and the other things running on the secure side, but you can do it. If you decide to run a secure and non-secure image, you have 2 binaries. You have to package them together in a way that both sides know where everything is. And what this means is that on an ARMv8M, the way the address map works is that you actually have aliases that specify whether or not it's a secure or non-secure address space. So every one of the peripherals and RAM and flash has 2 addresses. There's the non-secure and the secure. When you start to divvy up your flash and RAM, you actually have to say, okay, well, how much of my flash do I want for secure and how much do I want for non-secure? You lay it out in your address map, and then for the secure side, you have to start at those addresses. For the non-secure side, when you actually do the jump to the non-secure, you have to know what that address is, and not only that, the non-secure application, Zephyr, has to know what that address is. Today, we currently describe this in DTS. So if you go to Zephyr and you look at any one of the boards, you'll see that it has a device tree file that'll contain a RAM, flash, peripheral address map. This isn't going to be any different for ARMv8M. The complexity is that whatever you describe or use on the secure side, you also have to describe and use on the non-secure side using different address ranges, and not only that, different offsets. So if you set aside, let's say, 32K of RAM for secure, and let's say you have 96K of RAM for non-secure, the non-secure side is not only going to be a different address, it's going to be offset into that 32K into the RAM. And if you set up your configuration in a specific way, if you don't do that properly, one of 2 things happens. Either you get lucky and you somehow manage to get an address that you can use, or you have a violation and you get a fault. And you don't get very useful information back. The system just, you stop. So that's not very useful. So one of the problems that we have is we have to have a coherent description of the hardware. On the Zephyr side, we already use DT. We want to use device tree also in the TFM to describe this, and we want to use the same DTS. And one of the things one of the changes that's come in recently was support for the ranges property. And if you're familiar with DTS, that's great. If not, DTS just allows you to describe your hardware. The ranges property actually allows you to map the address based on some rules. So we can actually describe the hardware, the complete hardware, using one device tree file, but we can generate two outputs based off of whether or not it's secure and non-secure. So that's good. When an application developer decides how they want to divvy up the resources, that comes into play. You have to figure out which peripherals are owned by which, divvy up your flash and RAM, and all the numbers have to match up. One nice thing about using the same file, with the outputs, we can actually compare them and make sure that there's no overlap. That will save users a lot of problems. So this is one of the things that's currently in work. So to touch on all the items that we currently have in progress, there's some PRs out there for Musca support. Those still need, I think there's still a few comments that are outstanding. We're adding support for the MPS2. If you don't know what that is, that's one of the ARM development boards that has an FPGA on it. It allows you to load different models, so you can actually run more than just the M33 or M23. You can run a lot of other processors. We have multi-core work going on both the V7M and V8M side. There's a group or some individuals in LITE that are working on OpenAMP. We have one guy working on the IPC for the V7M, and we're going to be spooling up the V8M work since we do currently have a board that has two M33s on it. There's ongoing work with the device tree. Once we gets that'll be put in place about at the same time that the Musca is, because those two are kind of stuck together. And then we have some of the TFM improvements that we want to do. So TFM right now, it's in its early stages. There's some things that can be added, changed, improved. Some of the things that we have to kind of wrangle our heads around is some of the secure functions and kind of making it a little bit more modular. Ideally, from a Zephyr perspective, we'd really like to perhaps use Zephyr without the scheduler and without some of the pieces as the core, and then add in some of these TFM components, and that would be our secure image. The TFM today, I'm not sure if it really needs some OS primitives, but if it gets to the point where they do, you're going to have a selection of some RTOS that acts as the base. I think RTX is what they have some hooks in for right now. We really prefer that to be Zephyr. It's open source. And then we still have some of the ongoing work with the integration. So we want to make building Zephyr with TFM to be kind of seamless. That means, doing a make versus making Zephyr, creating an image, going over to TFM, creating an image, running some scripts to combine the images correctly. We don't want it to be that complicated, because the generic user is going to come in here and that's too much work for them to understand. They shouldn't have to understand that. Really what they should come in and say, okay, make Zephyr, make TFM, that goes over and makes a TFM image, and then package it and be done. So that's really the goal that we want when we get to the end. And I think that's it. So I added some links at the end. Last Monday, PSA opened up, they put their documents out, public documents. They're still, I think, in alpha, but all of the documents are available. So if you go to that site, you have to click on each one of their documents separately to download it. But they are out there, so that's good. So I would suggest, if people are interested in this, go download all the documents and take a look at it. They have some great information about PSA. They also have some really nice threat models, which are very useful. When you go and you actually create a product or you decide what you want to do, you really need to think about creating a threat model to understand what pieces of the system you need to protect and how you're going to do it. So their threat models are great examples. If you want to check out the trusted firmware itself, the code, there's the link to that. I think that's going to change. It's going to be moved somewhere else, I think under Linaro, but that is still accessible today. And I ran through a bunch of information. We're at the end, so we're at the I can field some questions. I'm sure there's quite a few. If you have a question, we need to get the mic to you so everybody can hear the question.
Please.
Right. So first question, in case of single core, the context switch, then it's a context switch.
Yes.
What is the overhead on V8 for that?
I don't think it's very high. They use some banked registers, so really it's I don't know, maybe one of the ARM guys has numbers on this, but I don't think it's very high. It's definitely not like doing an IPC call.
Okay, all right.
I haven't timed it. And really, the boards that we have aren't good candidates for timing it anyway.
I've seen on some T implementations, it could be quite high on Android phones, which leads me, do you see Zephyr moving away from TFM and all the way to T, or is TFM a spec that is that other architectures could possibly implement?
So the overarching documentation or process that they want people to use is PSA. TFM is merely an implementation that is PSA compliant. I think that's the language that ARM uses. They're very happy to say, if you want to implement whatever architecture, something that does the different requirements that PSA requires, then you would have a PSA compliant solution for that architecture as well. So I think the important part is that it adheres to the PSA. Any other questions? I don't know if that's good or bad. Okay, well, I guess we're finished. Thank you.